Welcome back to my YouTube channel. Today we will discuss a TIFR exam question. Question is given that A is a matrix, and then given A, then the matrix A0A, is diagonalizable if and only if which of the following condition is true. So now solution. Now if A is equal to 0 matrix, now option number A equal to 0 matrix, then this matrix A0A, that is equal to 0 0 0 0 matrix. So 0 matrix, and we already know that 0 matrix is diagonalizable. So A option is true. Now second option, if A equal to identity matrix, suppose this is 2 cross 2 matrix. So this matrix is given by 1 0 0 1 1 0 0 1 0 0 0 0 1 0 0 1. So eigenvalue of this matrix is 1 1 1 and 1. That is a rectangular matrix. So diagonal element are eigenvalues. So algebraic multiplicity of 1, eigenvalue 1 equal to 4. Now check the geometric multiplicity. So now A minus I, that is equal to 0 0 1 0 0 0 0 1 0 0 0 0 and 0 0 0 0. So rank of the A minus I equal to 2, because this is a 2 non-zero rows. So nullity of A minus I, that is equal to, this is a 4 cross 4 matrix, so 4 minus 2, that is equal to 2. So this implies geometric multiplicity of 1 equal to 2. Here AM of 1 not equal to GM, so this implies A is not diagonalizable. So option number B is false, and similarly option number C also C. So answer of the question is A. Already we discussed. Now prove in general. So now we prove this result by n equal to 2, for n equal to 2. So A is a 2 cross 2 matrix. So let values of A equal to alpha and beta. So here 3 cases are possible. If alpha beta equal to 0, so this implies A is nilpotent matrix. So also B equal to A 0A, and characteristic polynomial of B, so CBX, that is characteristic polynomial of B, this is equal to characteristic polynomial of A into characteristic polynomial of A. So this is equal to CX whole square. Characteristics polynomial of A whole square, characteristic polynomial of B equal to. So this implies eigenvalue values of B also 0 0 0 0. So this implies B is also a nilpotent matrix. So this and also given B is diagonalizable, this implies b equal to 0. Okay, so b equal to 0 implies a equal to 0. Okay, and converse is also true, already given. So in this case, when all eigenvalue are 0, then is true, a equal to 0 matrix. Okay, now eigenvalues are non-zero, alpha and beta not equal to 0. Okay, and if this eigenvalue are equal, that is alpha equal to beta. So if eigenvalues of alpha equal to beta, okay, equal, so eigenvalues of b, this equal to alpha 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 alpha. Okay, so minimal polynomial of b, that is equal to x minus alpha. Why? Because b is a diagonalizable. If b is diagonalizable, then minimal polynomial of b is distinct linear factor, so that is only x minus alpha. Okay, and by the Cayley-Hamilton theorems, we have we know that Cayley-Hamilton theorem say that the characteristic polynomial or minimal polynomial satisfy the matrix. Okay, so this implies MBB equal to 0. So this implies b minus alpha I equal to 0. So now put the value of b, that is equal to a 0a, okay, minus alpha 1001 equal to 0. So this implies a minus alpha, okay, and here a and 0, a minus alpha. So this equal to 0 0 0 0 matrix. Okay, so comparing this coefficient of both sides, so this implies from here a equal to 0. So a equal to 0 matrix. Okay, so this is also true when alpha equal to beta. Now if alpha not equal to beta, in this case, so characteristic minimal polynomial of beta, that is equal to x minus beta and x minus alpha. Minimal polynomial of b, that is equal to x minus alpha and x minus beta. Okay, linear factor, distinct linear factor, because b is diagonalizable. Now this implies b minus I beta into b minus I alpha equal to 0 matrix. Okay, by the Cayley-Hamilton theorems. So we have b square minus alpha beta into b plus alpha beta identity equal to 0. Okay, now put the value of b. So this implies a 0a into a 0a, okay, minus alpha plus beta into a 0a, that is equal to minus alpha beta identity. Okay, so this implies a square 2a square 0 into a square, okay, minus alpha plus beta, that is a 0a, okay, and this equal to minus alpha beta identity. Okay, so this implies a square minus alpha beta into a, and here 2a square minus alpha plus beta a, okay, and here also 0, and here a square minus alpha beta into a. Okay, so we only consider this coefficient. So comparing, we have 2a square minus alpha plus beta into a, that is equal to 0 matrix. Okay, so this implies a common. We have 2a minus alpha beta identity equal to 0 matrix. So here we have a equal to either a equal to 0 or 2a minus alpha plus beta identity equal to 0. So this implies a equal to alpha beta by 2 into identity. In both case, eigenvalue of a here 0 comma 0 and eigenvalue of this alpha plus beta by 2 and alpha plus beta by 2. In both case, eigenvalues are equal, which is a contradiction. Because we already given eigenvalue of a is not equal, okay, but we have eigenvalues is equal. In this case it's not possible. Okay, so only we conclude here, only if B is diagonalizable, this implies A equal to 0 matrix. Okay, in this above case, and A equal to 0 matrix, so this implies B equal to 0 matrix and B is diagonalizable and converse is easily true. So hence the proof. Okay, so answer of the question is A. Okay.